This is the video for exam practice session 5, where we will cover probability and Bayes sets representations. In this first question, we're looking at finding and selecting each of the expressions in which all the expressions are equal to 1, given no independence assumptions. So if we look at this first option, and we're summing over all the values of a, and because a is our unconditioned variable, we know that this is a valid probability distribution over the values of a, and so therefore when we sum over a, this is equal to 1. So this is a correct answer. However, when we're summing over the unconditioned variables, this is not necessarily equal to 1 because we're not summing over the unconditioned values. Looking at the second one, we have a joint probability distribution over a and b, and we have a double sum over a and b over all the values that all the values in this joint probability table. So when we sum over both of these, this is equal to 1. Now when we look at this one, we find that when we sum over a, like we saw in this first option, that will be equal to 1. However, when we sum over b, we actually will get something that's bigger than 1. So this is going to be a sum over b of 1, because if we swap this summations so that the summation over a comes first, that inner part will become 1, and then the outer part will be the summation over b of 1, and this will actually equal the cardinality of b, which is not equal to 1. Next, we see where we are multiplying probability of a and probability of b. And note that the probability of a only depends on the values of a and not on b. And similarly, probability that b equals little b does not depend on the value of little a. So this is also equal to the summation over a of the probability of a equals little a times the summation over the little values of b, that the probability of b is equal to little b. And we know that this first expression is equal to 1 because we're simply summing over the entries in the probability table, and the second entry is also equal to 1. So 1 times 1 is equal to 1. So this is equal to 1, which is correct. This next option doesn't equal to 1 because the first part is the summation over a, and this doesn't depend on a. So this first part will equal 1, but the second part does not necessarily equal to 1. So this is just equal to the probability that b equals little b. So that's not equal to 1. So this is our final answer. In part B, we want to find all the expressions that are equal to the probability of a, b, and c. And we can't make, given no independence assumptions. So let's first look at this first option. Here, this is actually exactly the chain rule. So we know that for what the chain rule says is that for any joint distribution over n variables, this is going to be equal to the probability of one of them times the probability of a second variable conditioned on that first, times the probability of the third variable conditioned on the first and the second, and so on and so forth. Or more compactly, this is equal to the product over the I variables of the probability of xi given x1 through xi minus 1. Whoops. So therefore, this first option is equal to the probability of a, b, and c. Now let's look at the second option. Here, this case will only be true, will only be equal to probability of a, b, and c if a and b are independent, because here you're conditioning on a and b, so therefore for this to be equal to probability of a, b, and c, this would need to be equal to the probability of a and b. And that's just given the definition of conditional independence, that probability of A, B, C over the probability of A and B is equal to the probability of C given A, B. And then if we bring this to the other side, then probability of A, B, and C is equal to the probability of C given A and B times the probability of A and B. However, that's not what we have here, so this is incorrect. This third option is similar to the above, except that the unconditioned variables are A and B, and the conditioned variable is C. And this does obey the law of conditional probability, or the product rule, so this answer is correct. The third option is actually the same as the second option, except instead of having probability of A times probability of B, it has a probability of A and B, which is true, is actually equal to probability of A, B, and C, without making any independence assumptions, so this is true. Actually, going back to this one, this makes the assumption that A is independent of B, if they were to be equal. Now this third option is also incorrect, because we know that this expression right here, probability of B given C times the probability of C, is equal to the probability of B comma C. And for this to be equal to probability of A, B, and C, we would need to multiply A given B and C times the probability of B, C. However, this only conditions on B and does not condition on C. However, this would be the correct answer. This would be true if A was independent of C given B. However, we can't make that assumption. Now this last option, if we expand it out, we'll find, I'll expand it out right here, we'll find that we get this expression right here is the probability of A, B, C divided by the probability of B and C. And similarly for this one, this is probability of ABC divided by the probability of AC, and this one is probability of ABC divided by the probability of AB. When you expand it all out and multiply it together, what you'll get is on the top, you'll get probability of ABC cubed divided by, on the bottom, you'll get probability of BC times probability of AC times probability of AB. And you can't simplify beyond that without making any independence assumptions, so therefore this answer is also not correct. In this third part, we're trying to find the expressions that are equal to the probability of A given BC. And we know that from the law of conditional probability, this is equal to the probability of A, B, and C divided by the probability of B and C. So we're looking for the expressions that are equivalent to this. So if we look at this first expression, the numerator is obviously correct. The denominator, on the other hand, is summing over A and has the joint probability over A and B and C on the inside of that summation. So when you sum over A, that's the same as marginalizing out A. So the result is that you get the probability of B and C on the bottom, and A is eliminated. So therefore, probability of A, B, and C divided by probability of B and C gives us the correct answer, without making any additional independence assumptions. Now for the second option, we can see that the denominator is exactly in the form that we want. The numerator has changed, but this is exactly the product rule, and we know that this numerator is equal to the probability of A, B, and C by the rules of conditional probability, so this is also a correct answer. All right, next let's look at this third option. So we have probability of probability of B given A and C times the probability of A given C. So the numerator is the probability of A and B conditioned on C, and we know that just from the product rule, because we have B given A times the probability of A, and all of it's conditioned on C. And in the denominator, we have the probability of B given C. that when we divide this out, both of them are conditioned on C, so our result will also be conditioned on C. But when we divide out the probability of A and B divided by probability of B, we now condition on B as well. So by the rules of conditional probability, the result is the probability of A given B and C, without making any additional assumption guarantees. So therefore, this option is also correct. Now in this third option, the denominator is what we want to be. However, the numerator is not equal to probability of A, B, and C because of this condition bar right here. If this was A and C instead of A conditioned on C, then it would be correct, but this numerator actually instead equals the probability of A and B conditioned on C, not the probability of A, B, and C. So this is not correct. In this fifth option, we have probability of B given A and C times the probability of C given A and B. This is not equal to probability of A, B, and C because both of them are conditioned on A and it doesn't simplify. So therefore, this is also an incorrect answer. And then lastly, this last option is comparing AB given C over B given A and C. So this is the same as the probability of A, B, and C divided by the probability of C. That's just the numerator times the probability of A, B, and C divided by the probability of A and C. And there's no way we can simplify this to come out to A given B and C without making independence assumptions. So this is also not correct, and that's our final answer. Now let's look at part D. So in this question, we're trying to find all the expressions that are equal to the probability of A given B, which we know will be just the probability of A and B divided by the probability of B, given that we know that A is independent of B given C. We have the probability of A given C times the probability of B given C divided by the probability of B. So on top, because A is independent of B given C, we know that this is the probability of A, B given C divided by the probability of B. However, this top part may not equal the probability of A and B because we don't know that A and B jointly are independent of C. We only know that A is independent of B conditioned on C. Therefore, this is not equivalent to probability of A given B without making an additional independence assumptions beyond this assumption. In the second option, the top is the same. The top is probability of A and B given C, and the bottom is probability of B given C. And this also doesn't give us the correct answer because we're still conditioning on C. The result, what this actually equals, is the probability of A given B and C. Because A and B are independent conditioned on C, this is actually equal to the probability of A given C, which is not equal to the probability of A given B. Now let's consider this third option here. So we know that these two first terms are equal to the probability of A and B given C, because we know A and B are independent given C. And the last term is the probability of C, and we're summing over all values of C. And the denominator is summing over all values of C, C prime in this case, and we have the probability of B and C. And so the top is probability of A, B, and C, summing over C. So the top is the probability of A and B. And the bottom, we're summing over C, over the values of C, and we have probability of B and C, so the bottom becomes probability of B. So this equals the probability of A given B. So this is a correct answer. All right, so here in this fourth option, we have on the top, because A and B are independent given C, this is the probability of A given C on top, and we also have probability of A given C on the bottom, so this is equal to 1. So that's not equal to probability of A given B in all cases. Now looking at this next option, we have probability of B given AC times probability of AC summed over C. So this is summing over the values of C, probability of A, B, and C. And we have the probability of B on the bottom. Similarly to this third option, this gives us probability of A and B divided by the probability of B, which is equal to the probability of A given B. So this is correct. Now let's look at this last option. So we have the probability of AC times the probability of B given C. We know that this term right here is equal to the probability of B given A and C, given that because we know that A is independent of B given C. So when we multiply that by the first term, probability of A and C, we get that the top is the sum over C of the probability of A, B, and C. And on the bottom, we have summing over C, the probability of A, B, and C. Oops. Probability of A, B, and C. So this is equal to 1, which is not equal to the probability of A given B. So that's our final answer. Now let's look at this last part. So we're looking for things that are equal to the probability of A, B, and C, given that we know that A is independent of B given C, and A is independent of C. So in this first case, we have probability of A times probability of B times probability of C. And the only way that this will be true, and it will be equal to probability of A, B, and C, is if A is independent of C, which we know is true, A is independent of B, and B is independent of C. And that is not true. We can't show, there's no way to show that B is independent of C. Therefore, this is not a correct answer. Now let's look at the second option. So here we have probability of A times the probability of B and C. We actually know that the probability of A is equal to the probability of A given C by this second assumption right here. And we know that the probability of A given C is equal to the probability of A given B and C, because we know that A is independent of B given C. So therefore what this expression becomes is the probability of A given B and C times the probability of B and C. Therefore, when we multiply these two together, we will get probability of A, B, and C, which is true. Now for this next problem, we know that this right here is equal to the probability of B and C. And now we care about what this part is right here. And if we can show that this is equal to the probability of A given B and C, just as in the above, or if it's equal to probability of A given C or probability of A, then we've shown that it equals the probability of A, B, and C. So what we care about is whether or not A given B is equal to the probability of A. And that's true if A and B are independent. And we can actually show that this is true. So the way to show this is we start with the probability of A and B, and we know trivially that this is equal to summing over C of the probability of A, B, and C, which is equal to summing over C of the probability of A and B given C times the probability of C. Next, we can split this first term up using the fact that A and B are independent given C, and this will become probability of A given C times the probability of B given C times our last term, probability of C, and we're still summing over C. Now from here, note that A is independent of C, so this first term is just equal to the probability of A. So we can move that out of the sum, and we can set this equal to the probability of A times the sum over C of the probability of B given C times the probability of C. Now we can combine these two terms, B given C times the probability of C, and what we'll get is the probability of A times the sum over C of the probability of B and C. Summing over C. And when we do this, this is equal to the probability of A times the probability of B. So therefore, we've just shown that the probability of A and B is equal to the probability of A times the probability of B. And therefore, A is independent of B. So we now know that since A is independent of B, A given B is just equal to the probability of A. And we showed above that we have probability of A times the probability of BC. Because the probability of A is equal to the probability of A given BC, this answer equals the probability of A, B, and C. Now let's look at our other options. So this fourth option right here, we actually saw before, and we saw that this is equal to the probability of A, B, and C cubed over the probability of A and B times the probability of A and C times the probability of B and C. And we can't simplify this to just come out to the probability of A, B, and C with the independence assumptions that we have. So this is not a correct answer. Now let's look at this, this fifth option. So right here we have the probability of B and C. And on the left we have the probability of A given C, and before we know that this is equal to the probability of A given B and C. And the probability of A given B and C times the probability of BC is equal to the probability of A, B, and C. So this is true. Lastly, this last option, because A and B are independent given C, this is equal to the probability of A and B given C, which is not equal to the probability of A, B, and C. So this is not true. And that's it for question 1. In this question, we're trying to figure out which of the following statements are true given without making any additional assumptions given the graph. So in this first option, we have probability of A given C and E is equal to the probability of A given C. And this is only true if A is independent of E given C. And if we look at the graph, so if we are conditioning on our C variable, we want to figure out whether A is independent of E given C. And we can see that this path right here is inactive by the rules of d-separation because this node is observed. And we also need to check all the other paths, and there's only one other undirected path to E, and that is through D, G, and F. And we can see that by this V structure right here, this is also an inactive path. So therefore, A and E must be independent. So this statement is true. Now looking at this second statement, we have A and E given G being equal to A given G times E given G. So this is true if A is independent of E conditioned on G. So in this case, we want to shade in this node, and we can look at all the undirected paths from A to E, and there's 2 of them. One is right here, which is active, and this other path over here is also active. However, we only need one of the paths to be active for them to be dependent, and therefore we know that this statement is not true. Now let's look at this third one. So this one is true if A is independent of B. And by looking at the graph, actually it's not just that A is independent of B, it's A is independent on the event that B takes on the value little b, which is just a slightly more specific case than A being independent of B. And we can see from the graph that A is independent of B because this path right here is inactive. So therefore, even the more specific case of B taking on a single value is also true. So this is true. In this next question, we have A given B and G is equal to the probability of A given G. So this is equivalent to saying that A is independent of B given G. So in this case, we are conditioning on G. So we'll shade in that node, and we'll look at whether this path is active or inactive. Because we are conditioning on because we're conditioning on a node right here, this path becomes active by the rules of d-separation. So therefore, these nodes are not independent in this scenario. So this is not true. Next, we're looking at the second to last statement right here. So this is saying that E is independent of G given D. So in this case, we are conditioning on D, and we want to look at the paths from E to G. And there's two paths. One of the paths is this right here, and one of the paths is here. We know that this path right here is active based on the rules of d-separation. And so therefore we don't even have to look at this other path. And it actually turns out that that other path is inactive because of this structure right here. But either way, because this path is active, we know that E and G are dependent and not independent, conditioned on D. So this is not true. Lastly, we have AB given F being equal to A given F times B given F, and this is saying that A is independent of B given F. So if we shade in our variable F, we're looking at whether or not A and B are independent. So in this case, because this arrow is pointing in this direction, it's not considered part of, doesn't fall under the case where you have a node right here and a condition node right here. In this case, they would be dependent, but since this node is going in this direction and both of these variables are unobserved, then we know that these two variables are indeed independent. So this is true. And that's the final answer. Okay, now in question 3, we're trying to figure out which of the Bayes nets, which of these above networks can represent the distributions that B1 can represent without making any additional assumptions or any additional assumptions about variables being independent. So the first thing to do is to think about what distribution is represented by this Bayes net. And we know that we have a formula that the joint probability over all the variables, which in this case is probability of A, B, C, and D, is equal to the product of some node I, say the nodes are xi, of the probability of xi given the parents of that node. So then for this graph, we get that we have the probability of C given A, B, and D, because those are each of its parents, times the probability of A, because A doesn't have any parents, probability of B, because B also doesn't have any parents, times the probability of D, because D also doesn't have any parents. So this is the probability distributions that this graphical model, that this Bayes net can represent. And so therefore it can represent any distribution where A and B are independent, B and D are independent, A and D are independent. And we can see that all from the Bayes net structure. It can also represent more complex relationships where whenever you condition on C, the other variables A, B, and D are not independent. So this first question, we are looking at which distributions G1 through G8 are able to represent at least one distribution that B1 can represent. So let's first look at G1. So in this case, this distribution, because none of the nodes are connected, is just P of A times P of B times P of C times P of D. In this case, all of the variables are independent. And if you think about it, this representation, B1, can also represent that probability distribution where all the variables are independent, because if you just set P of C given A, B, D equal to the function P of C, then that distribution where all the variables are independent can be represented by B1. And it's actually true that all of these distributions can represent that one distribution where the sets of distributions in which all of the variables are independent and can be factored as the probability of A times the probability of B times the probability of C times the probability of D. So therefore, it's actually true that all of these networks can represent at least one distribution that B1 is able to represent, because B1 can represent this mutually independent, this distribution where all the variables are mutually independent, as can all of the graphical variables above. So the correct answer is that all of these graphs are able to represent at least one distribution that B1 is able to represent. Next, let's look at part 2. So this is asking which of the distributions are able to represent all of the distributions that B1 can represent. So B1 can actually represent distributions that are more complicated than just the distribution that we discussed in this above question. So for example, if we look at G1, this distribution cannot represent the distribution that B1 can represent, because the probability of C might depend on the values of A, B, and D. So this is not correct. This network basically makes the assumption that A is independent of C, for example, and this independence assumption isn't made in this graph, so therefore it's not able to represent all the distributions that B1 can represent. Now if we look at G2, we can also find that this graph actually makes the same assumption that A is independent of C, so therefore it can't represent all the distributions that B1 is able to represent. Now for G3, if we look at this graph and compare it to B1, we'll see that an additional assumption that's made is that D and C are independent conditioned on A. So if we conditioned on this variable A right here, that would separate D and C. So therefore, D is independent of C given A. And so therefore, because if you look in this graph, if you condition on A, D and C are not independent. So that's an additional assumption that's made. So this G3 is not correct. Now let's look at G4. So this graph actually makes the same assumption as before. For conditioning on A, we find that D is independent of C. So this G4 is also not valid. Now looking at G5. So in this case, if we So in this case, all the arrows are pointing away from C. So if we condition on C, then we will get that A and D are independent, for example. And in this case, if we condition on C, A and D actually do become dependent. And also more simply, in this, However, in this graph, A and D are not independent given C. This is an additional independency assumption that G5 makes that B1 does not make. So therefore, it's not able to represent all the distributions that B1 can represent. Next, let's look at G6. So in this case, this graph actually makes very little conditional independency assumptions because there are a lot of arrows, and however, there is one assumption that it does make, and that is if you condition on both A and C, then B and D become independent by the rules of D separation. So we know that B is independent of D conditioned on both A and C. However, if we look at B1 right here, and if we condition on both A and both C, B and D are not independent because of the V structure or a common effect. So therefore, this option is not correct. Next, let's look at G7. So this graph, it's hard to tell if it makes any conditional independency assumptions just by looking at it. However, what we can do is we can write out the distribution by this equation right here. And we'll find that, so D doesn't have any parents, so this distribution is equal to the probability of D times the probability of C given D, because C only has one parent, times the probability of A given C and D, because A's parents, probability of A given C, D, and B times the probability of B given C and D. And we can see that this is actually exactly the chain rule. We're taking one variable, multiplying the probability, multiplying that by the probability of a second variable given that first variable, and so on for the rest of the chain rule. And because this representation is exactly the chain rule, it doesn't make any independency assumptions because it can't factor beyond the chain rule. Therefore, this is actually making no independence assumptions, and therefore it can represent all the distributions that B1 can represent without making any additional independence assumptions because it doesn't make any. So this is a correct option. Now let's look at G8. So in this case, if we write out the probability distribution, we get the probability of B times the probability of A given B times the probability of D given A times the probability of C given A, B, and D. And we'll see that this term right here, C given A, B, and D, is exactly the same as this term right here. The probability of B is also the same, and then the probability of A and the probability of D are actually more complex and make fewer independence assumptions than B1 makes. However, there are no cases in which it makes additional independence assumptions that B1 makes. So therefore, this is also a correct answer. Now let's look at part B. So this is a question identical to the first, except we have a new graph now, and now this graph is B2, and we can write the distribution just like we wrote before. In this case, the probability of A, B, C, and D is equal to the probability of B times the probability of A given B times the probability of C given A times the probability of D conditioned on A. And so thinking about this first question, part I, this is exactly the same as before, in which I'm concerned about one distribution that B2 can represent. And if we think as before, we can think about the distribution where all the variables are independent. So we have the probability of A times the probability of B times the probability of C times the probability of D. And this representation, this probability distribution can be represented by B2, and it can also be represented by all of the graphs G1 through G8 above. So the correct answer is that all of the graphs are able to represent at least one distribution that B2 is able to represent. Okay, so now in part 2, we're looking again at now the graphs that are able to represent all distributions that B2 is able to represent. So similarly to before, we're looking at which graphs make additional conditional and dependency assumptions that B2 does not make. So if we scroll up here, we can see that we can reuse a lot of the ones that we computed before. So in this first graph, it makes the assumption that A is independent of C as well as G2, and this is an assumption that B2 does not make. So neither G1 or G2 are able to represent all of the distributions that B2 is able to represent. Now let's look at G3. So in this graph, before we found that D is independent of C given A, and that's actually true for this graph as well. So that independence assumption is not additional on top of B2. However, this graph also makes the assumption that B is independent of D. And in this graph, B is not necessarily independent of D because of our D separation rules. So therefore, G3 is not valid for, it is not able to represent all the distributions that B2 can represent. So next let's look at G4. Before we found that D is independent of C given A. However, this distribution is not, this independency is represented in B2. And we can actually see that the only differences between G4 and B2 is that 2 of these arrows are swapped. And these arrows, what they do is they represent the structure that B and D are independent given A, that A and D are dependent, that B and A are dependent, and B and D are dependent. And if you swap these 2 arrows, that doesn't change any of that. B and D are still independent given A, and A and D are dependent, A and B are dependent, and B and D are dependent. So therefore, these 2 graphs actually represent identical probability distributions. And it's not always the case that when you swap the direction of some of the arrows, it will result in the same probability distribution. That's just a special case for this example. So in this case, G4 is able to represent all of the probability distributions that B2 is able to represent. Next, let's look at G5. So before we found that conditioned on C, A and D are independent in this graph. So if we look here, and we'll find that if we condition on C right here, A and D are not independent. They're still connected. So therefore, this graph is making an additional independence assumption. So it can't represent all the distributions. So this answer is not valid. Now let's look at G6. So in this case, the only independence assumption that this graph makes, as we found before, is that B is independent of D given A and C. And if we condition on A and C in this graph, we'll also find that B and D are independent. And actually that this graph is identical to B2 except for that it adds 2 arrows in the graph, one from B to C and one from C to D. Next, let's look at G7. So in this case, before we found that it's actually not making any independence or conditional independence assumptions. So therefore, it's always guaranteed to represent any probability distribution between these 4 variables, so that therefore it can represent all the distributions that B2 is able to represent. Lastly, let's look at G8. In this case, if we compare the probability distributions between this graph and the probability distribution of B1, we'll find that probability of B is the same and probability of A given B is the same, and probability of D given A is also the same. However, the probability of C given A is different, and in this case, C given A can also depend on B and D. So this distribution isn't making any additional independence assumptions and can actually represent more distributions than B2 can represent. So this answer is also correct in that G8 is also able to represent all the distributions that B2 is able to represent. And that is the final answer.